Hello students, today we are moving to our fourth module. Okay, so with the previous session we have completed the third module, that module dealing with normal shock and oblique shock. So today we are starting the fourth module. So fourth module is dealing with another kind of flow. So that particular flow is known as Fano flow. Fano flow. Okay. So you might be wondering what actually is Fano. What Fano, the word Fano means. Okay. So students, in the first module itself, I have told you that if a compressible fluid flow is happening due to some different driving potential. So the second module dealt with isentropic flow. There the driving potential was, what was that? Variation in area of the duct area. So the only driving potential in case of isentropic flow was variation in duct area. So that is why we have learned the nozzle and diffuser. And second one is friction as a driving potential. And third one is heat transfer as a driving potential. What actually is a driving potential means the sole reason for change of flow parameters. So that is what driving potential is meant by. So what is the reason for a change in flow parameters along a flow? So there are a lot of parameters like temperature, pressure, velocity. So what kind of reason is what is the actual reason for change in the flow parameters when a compressible fluid flow takes place in a duct? So in the case of isentropic flow, it is actually the variation in the cross section or duct area. Another reason is friction due to the wall. Third one is heat transfer. So heat transfer may change the flow parameters. And the fourth one is mass addition of mass addition. So students, there are a lot of practical situations where the effect of wall friction is small compared to the effect of wall friction. So this is friction due to wall. Okay, so there are a lot of practical flow situations where the effect of wall friction is small compared to the effect produced due to other driving potentials like this change in area, transfer of heat, mass addition. Okay, so effect of wall is not that much comparable with all the other three driving potential. So in such cases, the result of analysis with the assumption of frictionless flow. So where the case where effect of friction is negligible or small compared to other driving potential, such analysis can be done based on assumption of frictionless flow. So such assumption won't make any deviation from the real situation. So such studies will always almost will be in matching it. It will match with the real situation. So the situations where wall friction is effect due to wall friction is small compared to the effect caused by other three factors. Such cases can be approximated as frictionless flow. So in those cases, the results generated will be very close to the real life results. But there are certain cases where when the effect of friction is neglected, uh, those cases where the effect of friction is neglected, which gives unrealistic results. Okay, so in such cases we have to introduce the friction factor because friction is acting. So when you introduce friction factor or friction due to wall as a factor in the flow, such flow is known as Fano flow. Fano flow. So when friction plays a major role in change in the determining the change in the flow parameters, where friction is the sole driving potential. Such a flow is known as Fano flow. So have you understood what is Fano flow? Fano flow are those flows where friction takes a major role, or friction is the driving potential for change in the flow parameters. So such flows are called Fano flow. Hope you have understood. So okay, the Fano flow is actually not just any kind of flow with friction as a parameter. Friction as a driving potential cannot be called as a Fano flow, but Fano flow is defined as those flow a simple one dimension steady steady flow steady flow in which friction is the only driving potential driving potential for what? Driving potential for property variation for property variation property change. Okay, so important point is that any type of flow with the friction as driving potential cannot be called as Fano flow. Fano flow is a one dimensional steady flow with the friction as the driving potential. So very important. So you should know what actually is Fano flow, how Fano flow is defined. Okay, so many practical situations involving short ducts can be approximated as a Fano flow. Those short ducts without heat transfer and mass addition can be approximated as a Fano flow. Okay, so the major assumptions for considering a friction flow as Fano flow is that it should assumptions for considering a friction flow as Fano flow are: first one, constant area duct. Area should be constant. Area of duct should be constant. So if there is a variation of area, means it will be a combination of, so it will be an isentropic flow. Okay, so it will isentropic flow, the duct area is varies. Okay, second, there should not be heat or work exchange. So Q equal to 0, work equal to 0. So it is diabatic process. No work transfer or heat transfer with the surrounding. Third one is no mass addition. Okay, or rejection. Okay. Fourth one is a general assumption. The gas should be perfect. Perfect gas. It should be a perfect gas. Flowing fluid should be perfect gas. And another assumption is that it should be one dimensional and steady. Flow should be one dimensional and steady flow. Okay, so there should not be any body forces negligible, because in momentum equation there shouldn't be any body force, only pressure force only should be there. And another point is no obstruction in the flow. The fluid should be free to flow. Right? Wall friction is the only driving potential. So the only driving potential. Okay, so these when these 8 assumptions are satisfied, such flow is known as Fano flow. Okay, for Fano flow all these 8 assumptions should be valid. Now what is a Fano line? Fano line. So when a Fano process when a Fano process is shown in shown in either H enthalpy specific column line or HS diagram, Muller diagram, then that line is called Fano line. Fano line depicts the Fano process in HS diagram or HV diagram. Okay, so that is Fano line. So you should know governing equation for this process. Governing equations. So students, you already know that wall friction due to viscosity is the major potential responsible for changes in the fluid properties in Fano flow, right? So the momentum equation, so where actually this friction comes in momentum equation. So there you should add some shear forces due to frictional effect in that particular momentum equation. Other simple the simple form of other governing equations like continuity equation. First one is continuity equation. Continuity equation is nothing but conservation of mass equation. Okay, the that equation will be rho a v equal to constant, or m dot mass flow rate is constant. And students, you have already learned in the assumption that area of duct is constant, so you can take rho v equal to m dot by a is equal to a constant, right? Rho v equal to m dot by a is equal to constant. So constant. So just term that constant is I will give a name for that constant as g. G is nothing but mass flow rate per unit area. Mass flow rate per unit area. Mass flow rate per unit area. Okay, per unit cross sectional area of duct, or it is also known as mass flux or mass velocity. Another name for G as mass flux or mass velocity. So it is G is also known as mass flux or mass velocity. How it is defined? It is defined as mass flow rate m dot per unit area. Okay, so that is G. So now we will move to our conservation of energy equation. So leave momentum equation. Momentum equation will be a bit complex because it includes shear stress, the friction factor and all. So in conservation of energy equation, you can see that since there is no heat transfer or work transfer, you can write it as h plus v square. If you neglect the elevation effects, h plus v square by 2 is constant for any state. So if h plus v square by 2 is constant, means it can be termed as h0. H0 is static enthalpy. So stagnation enthalpy. So stagnation enthalpy is constant for the flow, the state of flow at any point, right? So h plus v square by 2 is constant, means h plus v square by 2 equal to h0 is a constant. H0, stagnation enthalpy, is constant. So students, from the previous equation, so from here you can write v equal to g by rho, right? V equal to g by rho. Velocity can be written as g by rho. So you can substitute for velocity here. So h plus g by rho whole square by 2 is h0 is constant, right? Or h plus g square by 2 rho square is equal to h0 equal to constant. So students, what is 1 by rho? 1 by rho is specific volume, right? So you can see from here h0 is a function of g and h0 is a function of here you can see that here you can see that since h0 is constant and for a constant g, h and rho varies or h and specific volume varies, right? So you can get a constant h0 for various combination of h and rho if g is also constant. If g is constant, h0 is already constant, so you can get h0 with different combinations of different combinations of h and rho or or specific volume, right? Because specific volume is 1 by rho. Okay, so thus this particular equation establishes a unique relationship between enthalpy h and specific volume v for specified values of mass flux g. So for a particular value of g, there will be a particular not different there will be a particular combination of h and rho. Okay, because for a particular value of h and sorry, for a particular value of h and rho, for a particular value of g, there will be a combination of h and rho to get a constant h0, right? So that is why I can plot this equation and energy equation in HV plane, H specific volume plane. So students, you know there is a constant H0, right? H0 is constant for a particular flow. So if you plot this equation, you can see that H plus G square by 2 rho square equals H0. You will get these kind of, for a particular G, the curve will be like this. Okay, curve will be like this. This is G1. For another G, let it be G2. This will be the curve. So another G, G3. So students, you have to note that G1 will be greater than G2 greater than G3. Sorry. G3 will be greater than G2 greater than G1. So mass flux increases. G increases towards this direction. G increases towards the left direction. So these lines are known as Fano lines. Fano lines for different mass flux. So if you take this particular line, so this particular line has got a particular G1, right? Particular G1. So if you increase G2, the flow with the same H0. The line gets displaced to leftwards, and again G3 here. Okay. So if you increase G, it will get displaced to left side. So these are Fano flows for a particular case. So for this particular, so here one particular H1 and V1, and at another point you will get H2 and corresponding V2. Okay, so at different points in the flow for that particular G1, you can find H1 and V1. Enthalpy, static enthalpy and specific volume. Okay. So students, here we have discussed Fano lines in the case of HV diagram, but it is more convenient to plot Fano line in HS diagram. So we have been familiar using HS diagram, right? Fano line in HS enthalpy entropy diagram. So how can we plot this? We will use the functional relationship between enthalpy, entropy and density and all. So such curves in HS diagram looks like this. Students, HS diagram for a constant H0. So for a particular flow in a duct, H0 will always remains constant. So for different mass flux, okay, for different mass flux, this will, the Fano flow looks like this, okay. So these are different Fano flows with different mass flux. So mass flux increases towards left, okay. So the shape of the Fano flow looks like this, very important. So here the shape of the Fano flow is like this, and when it comes to STS diagram, this is like this, okay. So students, now look at this. If you take a point here, so through this point the pressure will be P1. This is point 1, the pressure through P1. This P1 is a static enthalpy. Static pressure at state 1 or point 1 for particular mass flux G1. So if you take the corresponding value in H0 line, that particular pressure will be P0, stagnation pressure, okay, stagnation pressure. This is 0, 1, right? That is how you find stagnation pressure and stagnation enthalpy. Okay, so here if you take, so point 2 is having a static pressure P2 and a corresponding stagnation pressure P02, okay. So P02 will be lower than P01, P02 will be less than P01, okay. P2 will be less than P1. So students, this is how mass flux, okay, this is how a Fano line looks like in a HS plane, okay. So students, if this is the G1 is the mass flux or mass velocity in this curve, G2 will be the mass flux here, G3, and G3 will be greater than G2, greater than G1, okay. Students, have a look at this one particular line, one particular Fano line, okay. So let this be A, some C here, some B here, okay. So students, I am what do you understand from this particular line with the mass flux G1 and having a stagnation enthalpy H0. So students, the Fano line represents all the state points in this Fano line represents different states with same mass flux G1 and same stagnation enthalpy H0, right? So a Fano line represents this, all the points in the Fano line represents different states with the same velocity and same stagnation enthalpy, same mass velocity and same stagnation enthalpy, but different static enthalpy. Here it will be H1, and here it will be H2. So static enthalpy differs and entropy also differs. Entropy varies, maybe density or small v, specific volume varies. All these properties varies, but G1 remains constant and H0 remains constant. So the the different points corresponding to different states with the same velocity, same mass velocity and same stagnation enthalpy. Understood? Understood? Okay. Now, from the figure, it can be seen that Fano line gives no information regarding the distance the fluid must travel to attain any of the thermodynamic states lying on that Fano line. Okay, so there is no such information regarding the distance the fluid should travel to attain a particular thermodynamic state. Okay, So the length of the constant area passage or duct required for attaining a state on that Fano line depends upon the entropy gradient and all. So this entropy gradient depends upon wall friction. Okay. So for the time being, you just leave that. That is a bit complex idea. So now you can see that shape of the Fano line on the HS diagram is such that it passes through a state top. So here students, you can see that there is an a maximum entropy point. So this shape is in such a way that the line passes through a state of maximum entropy. That point is, that particular state is C, right? So you have seen that Fano line passes through a maximum entropy point or maximum entropy state, right? The point of maximum entropy is denoted here as C on this particular curve. Okay. Now, students, since this process is having friction, so this is based on friction. If there is friction, the process will be irreversible, right? Irreversible, because friction is a dissipating phenomena, so the process will be irreversible. But since q is equal to 0, this is adiabatic, right? Adiabatic process. So this process, Fano process, will be an irreversible adiabatic process. But for irreversible adiabatic process, entropy always increase, right? Entropy, entropy always increase. It can never decrease. If entropy decreases, students, if entropy S decreases means it will be a violation of second law of TD, because in case of irreversible adiabatic process, S should always increase, right? So in this figure, S increase means the direction of the process should be towards right. So from the process direction should always be A to C. So C to A is not possible. Similarly, the process should be B to C. Okay. So C to B is never possible. So students, the total process A B is, there is no such process called there is no such process happening from A to B. Either it should be from A to C, or it should be from B to C. So there is no such a complete process like A to B or C to A. So C to A not possible. C to B is not possible, or A to B along this line is not possible. Only possible is only possible process is only possible process is from A to C this direction and B to C this direction. Why? Because entropy should always increase. So entropy only increases towards right. It never increases towards left. Okay, so any process towards the left side will be a violation of second law of TD. Okay, so this is how the Fano line is defined. Okay, Fano line consists of two branches, A to C and B to C. So students, now in this figure, the upper branch A to C, the upper branch is represented by A to C, right? So and the lower branch is B to C. So for all the points along the upper branch AC, the gas velocity. So here the gas velocity is higher than sonic velocity. Sorry, the lower than. So here this part is subsonic flow. Subsonic flow. Subsonic flow. And this branch is supersonic flow. Supersonic. So A to C is subsonic. B to C is Mach number greater than 1. Here Mach number less than 1. This is supersonic, this is subsonic. Okay. So I will explain how that how why that process is like how why that line is divided into two branches, and how upper branch is subsonic and lower branch is supersonic and all in next session. Okay, so for the time being, you just understand that the upper branch is where the velocity of the gas is below sonic velocity, and lower branches will be the state corresponding to the situation where the gas velocity is higher than the sonic velocity. That is, a supersonic flow will be represented by the lower branch, and a subsonic flow is represented by upper branch. Okay. So, and students, this particular flow where this particular point where entropy is maximum will be having a Mach number of unity. That here the process will become sonic. Okay. So due to the restriction imposed by the second law of thermodynamics, the process in the direction C2A or C2B is not possible. Okay, so I think you got a, a small or a brief idea about what actually is Fano flow, and how a Fano flow is represented as a Fano line in HV diagram and HS diagram, and why this HS diagram is divided into two, what actually is the upper branch, what actually is the lower branch. Okay, why the entropy, why the process like C to A and C to B is not happening and all. You got an idea, right? So with this, I will wind up this particular session. Thank you.